When we're talking about organic chemistry, functional groups become a really key feature. They're going to determine what kind of molecule it is, which often determines what kind of reactions it can do, and will always determine how we name it, the nomenclature of it. And those bits and pieces are going to be really important in what we do with organic nomenclature or with organic chemistry. So let's take some time to talk about functional groups. I'm going to have a big long list of groups and several examples of each. The examples are not a complete list at all, and I'm going to try and focus on the important parts of it so you have several examples without needing to write them all down. Well, first we need to know what a functional group is so we can recognize one. It's going to be a grouping of atoms that determine that allow us to classify a compound. So, carbon atoms, or carbon atoms attached to oxygen atoms, or carbon atoms attached to other carbon atoms with a double bond or with a triple bond. So either grouping of atoms or a type of bond involved. And as I mentioned before, it's going to help determine chemical and physical properties, and the functional group is going to do something about the nomenclature. Okay, so here's our list of the different functional groups. Some are going to be really important for us, some are going to be less important for us, but alkane is our base model. It's going to have only carbons, atoms, and hydrogen atoms, so it's sometimes called a hydrocarbon. It's sometimes called a saturated hydrocarbon because all of the carbons are single bonded, so carbon, single bond, carbon, single bond, carbon, single bond, carbon. The simplest one is here, and again, maybe or maybe not, and that should be written down. I'll let you decide. It's going to be the least likely one you're going to see. A more likely one is here. Now again, we would never write it as just carbon atoms because every carbon atom has 4 bonds and we have to include them all. So it's more the example on the right that you would see, but I wanted to point out the carbon skeleton chain where it's all carbon, single bond, carbon, single bond, carbon. And we can have branches and so on, but they're still all alkanes because everything that's there is a carbon atom and it's all single bonded. You can also have those wrap around and form a ring. And on the far right here is a shorthand notation that we'll use to represent rings where every point is a carbon atom, every line is a bond, and the hydrogen atoms are just implied. Next up is alkenes. And alkenes also are hydrocarbons. But the key difference with an alkene is that they're going to have a carbon-carbon double bond. And what's important to realize is that while on this first example the carbon-carbon double bond is pretty obvious, on other examples the carbon-carbon double bond is just one thing on a much larger chain. And it wouldn't matter. These compounds are still alkenes because they have a carbon-carbon double bond. And these two, for example, would actually be very similar. They both have 4 carbons. It's just where that double bond is positioned. That's going to become important later when we talk about nomenclature. This last example, again, is really long. I shouldn't say again because I didn't say that before, but of all the carbon-carbon single bonds that are going on, it's the double bond that identifies it as an alkene. That's how important functional groups are. Next one is the alkyne. And the alkyne is a carbon-carbon triple bond on a thing that just has carbon and hydrogen atoms. So it would be considered a hydrocarbon. Alkynes and alkenes are considered to be unsaturated hydrocarbons compared to the saturated hydrocarbon. So a very simple example, moving up to a larger example, and again, the examples aren't so important. It's identifying the carbon-carbon triple bond as a functional group. Moving on to an alkyl halide, you may remember halide from halogens, which means you've got a group 17 atom, fluorine, chlorine, bromine, or iodine. For our purposes, chlorine and bromine are going to be the most common ones that we use. And as long as it's somewhere on the chain, that thing is going to be an alkyl halide, even if it's just one thing on a bigger piece. And yes, if you're wondering, I can put a chlorine, bromine, or other halogen onto an alkene. I just haven't got that at this point. We won't worry about doubling up our functional groups too much just yet. Moving on to alcohols and ethers, and we'll kind of group them together, but for our purposes, ethers are going to become a really minor player. They're sometimes considered to be organic derivatives or organic versions of water. And I know what you're thinking, stop. Here's start with water. Water, oxygen with 2 hydrogens. If I replace a hydrogen with a carbon unit, I'll get an alcohol, whether it's 1 carbon or 20 carbons. If I replace the other hydrogen with a carbon unit, again, it can be as many carbons as I want, I now have an ether. Alcohols can further be divided up into primary or secondary or tertiary. That's not going to be a big important thing for us. It'll come up in a lab that we do. But basically, if you look at the carbon attached to the OH, you look at that carbon that makes up the carbon of the functional group, and you look to see how many carbons are attached to it. So in a primary alcohol, that carbon of the alcohol group has 1 carbon attached to it. Secondary, the carbon of the functional group has 2 carbons. In a tertiary, the carbon of the functional group has 3. That's it. Amines. Amines are now considered organic derivatives of ammonia. And I know what you're thinking. Stop. But if I take ammonia and I start replacing hydrogen groups, or sorry, hydrogen atoms with carbon groups, I now have amines. Now, different from alcohol, ether, is that they're all amines. I don't change the name in any way, shape, or form. And that means that I can have an amine hanging off of a chain, or I can have it in the middle of a chain. We're not going to spend a lot of time with amines, so if you're trying to write down examples, there's no need to get them all. We're not going to spend a lot of time with them. We will pay attention to aldehydes and ketones. And I want to caution you because aldehydes and ketones are sometimes easily mixed up. And what it comes down to is position. So they both have what's called a carbonyl group. Now you may have heard it pronounced differently, carbonyl or carbonyl or something like that. I always call it carbonyl because that's correct. If that carbonyl group is right on the end of a chain, one end or the other, it's going to be an aldehyde. And if it's not on the end, but somewhere in the middle-ish, then it's going to be a ketone. And that's it, just position. So you find the carbon attached to the double bond oxygen, and you look left and right. If one side of that carbon atom is a hydrogen, it's an aldehyde. If both sides are carbons, it's a ketone. Carboxylic acid, once we start talking about carboxylic acids and all the functional groups remaining now, we have to look a little bit beyond because we start to get functional groups where it looks like it could be this or a combination of that, and it's usually just going to be a bigger functional group. So carboxylic acid, is actually acidic. Who would have thought? But it has what's called a carboxyl group. Now, I'm not going to use that term all that often, but if you were in biology and you learn to identify these things by the carboxyl group, this is it. This is the carboxylic acid. And the carboxylic acid functional group, you'll notice it has a double bond oxygen, like aldehydes and ketones, but then beside that it has an OH group. So it's not a combination of a ketone alcohol or an aldehyde alcohol. It's a different functional group, carboxylic acid. Esters, we have to look a little bit farther again because and we don't really care that they're sometimes considered an organic salt, but we'll come back to that later. They have carbon double bond oxygen followed by an oxygen, so far we're kind of like a carboxylic acid, but that is followed by a carbon. And again, I can have a big carbon group, I could have a small carbon group, and it wouldn't matter, it would still be an ester. I could have an ester forming in a ring as well, where the carbon double bond oxygen followed by an oxygen followed by a carbon again. Amides, much like amines, we're not going to pay that much attention to amides, but I do want to point them out for 2 reasons. 1, functional group recognition. 2, if you took biology, they may look kind of familiar. So with an amide, carbon double bond oxygen followed by a nitrogen followed by, well, depends. Is it followed by a hydrogen or is it followed by carbons? Good news, doesn't matter. It's still going to be an amide. Now, I want to point out one more. This particular compound here is not an amide, but you might recognize it as a amino acid. So it has an amino group, the NH2 group on one end, and the carboxylic acid group on the other end. That's where we get the amino acid. And if I start putting a bunch of those together into a bit of a chain, now I have amide groups. And if you took biology, you may have learned that this is the building up of a protein. Okay, whirlwind tour of functional groups, but those are the ones that we're going to need to know. We'll do nomenclature of most of them. We'll do reactions with most of them. And then we need to know our recognized functional groups so that we can do all that. And here are the things that you should be able to do after watching this video. And after that, it's just getting more and more practice with them. So more and more work. There you go.